Now that you've been introduced to what the concept of integrals means, we're ready for the fundamental theorem of calculus. So here's our setup. Let's say that I have some function, y equals f of t. I'm using my horizontal axis, my independent variable, to be t, because I'm using the variable x to represent values on that axis. So let me get an arrow, point to some stuff. So the integral of f of t dt from a to x is going to represent the area under this curve above the x-axis between t equals a and t equals x. So I can shade that area right there. And furthermore, I'm going to let that area be a function, capital A sub f of x, meaning as I move x along this axis, this area is going to change. So this capital A of sub f of x is going to represent the area that I get. So when x is equal to a, then a of x would, or a of a will equal 0, because there's no area, and so on. So as I change values for x, I'm going to get different amounts of area, and I have a function, I'll call this the area function, based on this integral. Okay, so that's the setup. So you might need to go back in a little bit and revisit that idea just to make sure you understand it. All right, so I would like to find the difference between the area function of x plus h, which is going to be, let's do it in a different color, that's going to be the area of this. And I want to subtract off the area function evaluated at x, and that's going to be the red amount. So I want to take the green amount minus the red amount, and what that's going to leave me with is, let's do it in, how about purple? That's going to leave me with this area right here. And so that's what this expression represents, this thin amount here. So how am I going to do this? Well, I know that I can approximate using rectangles. So let's say, for example, that I decide to use a lower rectangle, and it'll just be one interval, and I want to go up to the function at x, and that'll be the height of my rectangle. And so the area of that rectangle is going to be the width, well, the width is just going to be h, times the height, which is going to be f of x. So f of x times h is going to be a little bit less than this area expression. On the other hand, if I decided to choose a bigger amount, let's say I use the right endpoint and I make a rectangle going up to the function and over, now the height is going to be f of x plus h, whatever that value is, times the width, which is also h. So that's going to be a little bit more than that area expression that I was trying to figure out. So f of x plus h times h. So this thin strip of purple shaded area here under the curve between x and x plus h, this amount here, is going to be greater than this rectangle and less than this rectangle. All right, so now let's work with this inequality. So first thing is, what if we divide everything by h? And what if I take the limit as h approaches 0? So in my picture, that means as x gets closer to x plus h, or x plus h gets closer to x, whichever way you want to look at it. If I take the limit of f of x as h approaches 0, less than the limit of this expression as h approaches 0, and that'll be less than the limit as h approaches 0 of f of x plus h. Now, let's get my arrow here. For this expression, as h approaches 0, this isn't even dependent upon h, so f of x is just going to remain f of x. On the other end of the inequality, the limit as h goes to 0 of f of x plus h is just going to be f of x. And then what about this expression? That should look familiar to you. The limit as h approaches 0 of a of x plus h minus a of x all over h. That's the definition of a derivative. And the derivative of what? That's the derivative of my function a, this area function. So I can just write this as a prime. All right, so now let's think about what does this actually mean? Well, that means if a prime is going to be greater than f of x, less than f, that means that a prime of x is actually going to equal f of x by the squeeze theorem. And so that's saying that the derivative of the area function is equal to f of x. Let's say that again. The derivative of the area function equals f of x. Now let's go back up to how we defined the area function and f of x. So let's go back up here. So the derivative of this equals this function here. Or another way of saying that is, the antiderivative of this function is our area function. And all of a sudden we're making a connection between derivatives and integrals. So this function, this integrand function, this function here, the area under this curve, the function that represents the area under this curve, is the antiderivative of this function f. All right, so let's look at formally what this is telling us. And there's two ways we can look at this. So if f is a continuous function, and obviously it's very important that it's continuous, and it's defined on an open interval I, which contains the value a, then the area function, capital A sub f, defined by this rule that we've already talked about, is defined for every x in that interval, and the derivative of the area function with respect to x is going to equal f of x. And that's a connection that you wouldn't normally have thought of, but the second version of this fundamental theorem of calculus is going to help us evaluate integrals now without using rectangular approximations. So if f is continuous on the closed interval AB, and capital F is any antiderivative of f, we know there's a whole family of antiderivatives because of the constant, then if we have an integral from a to b of f of x dx, that's going to equal, or in other words, we can evaluate it by taking an antiderivative, evaluate it at b, and then evaluate the antiderivative at a, and subtract them, and we'll get the value of the integral, or the area under the curve. So let's look at some examples and see how this works for us. Let's evaluate the integral from 1 to 2 of 3x squared dx. So first we need an antiderivative of 3x squared. Well, that's going to be x cubed. And the way we'll write this is we'll write the antiderivative, and we'll put a vertical line, segment, and we'll put the limits of integration. And then what we're going to do is we're going to evaluate, point with an arrow here, we're going to evaluate this antiderivative at the upper limit, and then minus, we'll evaluate this at the lower limit. So I'm going to plug in 2 first, and then I'll plug in 1 and subtract. So I'm going to do 2 to the third power minus, I don't know why I switched colors on that, minus 1 to the third power. Switch back. And so that's going to equal 8 minus 1 is 7. So the area under the curve 3x squared between 1 and 2 is equal to 7. Now you might ask, well, what could I have used a different antiderivative? Sure, I could have used x cubed plus, how about 4.78? Well, what happens when I evaluate that? So I'm going to plug in the 2, and I'm going to get 2 cubed plus 4.78 minus, and then I'll plug in the 1, and I get 1 cubed plus 4.78. And so you can see what's going to happen. The constants are going to cancel out. So it's not even necessary to write the plus c for our antiderivative. It's easier just to write the antiderivative without any constant added on. All right, so let's look at another one. Evaluate, and this might be a good time to hit pause, work out your answer, and then verify, check, and see if you got it right. Okay, so we want an antiderivative. So the antiderivative we're going to use, 1/4 x to the 4th, plus any constant if you like. And we're going to go from negative 2 to 4. So first I'll plug in the 4, so I get 1/4, 4 to the 4th, minus 1/4, negative 2 to the 4th. Let me put some brackets here, although that's not necessary. I didn't mean to put them there. What I like to do is actually, that's not working out very nicely. There we go. I like to put brackets around it this way because as the antiderivatives get more complex, you're going to find that when you subtract, sometimes you tend to make some mistakes with terms that you're subtracting. So when we go ahead and work this out, what are we going to get? So 1/4, 4 to the 4th. One of the 4's cancels. 4 to the 3rd is 64. And then the negative to the 4th is going to become positive. That's 16 over 4 is 4. And so we should get 60. Now we could use our calculator and double check that. If I put in my function, which was x cubed, and just do a zoom 6, and I want to go from negative 2 to 4, so second, calculate the integral from negative 2 to 4, and you can see we get 60. So the calculator does a nice job of approximating. All right, let's go through another one. How about this one? The integral from 0 to 1 of e to the x. Well, that's going to equal the antiderivative, which is e to the x, evaluated from 0 to 1. So that's going to be e to the first minus e to the 0. E to the first is just e to the 0 is 1. So we get e minus 1, or about 1.178, or 1.78. All right, let's try another one. Keep going. Now we're on a roll. What's the antiderivative of 3? Well, that would be 3x, evaluated from 1 to e. So we're going to plug in the e, and then we'll plug in the 1, and so we get 3e minus 3. And so now we're able to use this fundamental theorem of calculus to get the exact answer for our integrals instead of approximating. All right, let's look at a few more. We already worked with this one in the past, so let's see what happens now when we use the fundamental theorem of calculus. The antiderivative of sine is negative cosine. And we're evaluating from 0 to pi over 2. So I'm going to plug in the pi over 2. See, this is where I like using brackets or parentheses. So negative cosine pi over 2 minus negative cosine of 0 cosine of pi over 2 is 0. And that becomes a plus, and the cosine of 0 is 1. So we get a positive 1 for an answer. Okay, go ahead and try this one. What's our antiderivative? It's the natural log of the absolute value of x. But since our integral is going from 1 to 4, it's okay if you just actually use parentheses there. And we're evaluating this from 1 to 4. So we're going to get the natural log of 4 minus the natural log of 1. The natural log of 1 is 0. E to the 0 is 1. So our final answer, simplified, is natural log of 4. All right, let's try one last one. Let's write out our antiderivative. That's going to be t squared plus t, evaluated from 1 to 4. So parentheses, let's plug in a 4. We get 4 squared plus 4 minus, now we plug in the 1 squared plus 1. So that's going to give us 20 minus 2, or 18. And there you have it. So it's important to distinguish now, we've looked at definite integrals, and the solution is a particular value. For example, the integral from 0 to pi of sine of x dx wound up equaling 2. We just did it from 0 to pi over 2 and we got 1. And because of the symmetry, we know from pi over 2 to pi is another 1, which gives us a total of 2. So we're getting a particular value. On the other hand, an indefinite integral does not have limits of integration, and so your solution is just a family of functions. So if I said, what's the integral of sine of x dx, not evaluating it anywhere, well, then that should give us the area function, which is an antiderivative. So the antiderivative is negative cosine of x plus any constant. So definite integrals, we get a particular value. Indefinite integrals, we get a family of functions.